Hi all, Mr. Pope from Grammar School for Boys, and in this probability and statistics session we're going to be looking at the product moment correlation coefficient. We're also going to be performing some hypothesis testing for it. From now on, whenever I'm talking about the product moment correlation coefficient, I am just going to refer to that as the PMCC, right? Short for product moment correlation coefficient. It's just a lot easier to say. Okay, what is it and what do you do? Well, suppose, okay, I've got a set of data. I've got a data set. Let's say this is X and Y. And let's suppose, I don't know, these orange dots, these orange crosses rather, are the data set. Suppose I've got something like this. Okay, now suppose I want to describe what's going on here. And what we've seen at GCSE is you probably would have used something along the lines of this would be a strong positive correlation, right? And I'm not going to go over what the different types of correlation look like. A positive means it's got a positive gradient. A negative correlation means the data set appears to have a negative gradient. And this is as if we were to draw a line of best fit going through it, like so. I'm just trying to think, have we done regression lines? Yes, we did. Linear regression modeling. Did that back in April. So you should be familiar with how to plot this regression line. And if this regression line appears to have a positive gradient, then yeah, we'd say it has a strong positive correlation. However, let's take it one step further. For example, what can you tell me about positive correlations? Well, I mean, if I just look purely at the x-coordinates, the x is positive here and the y-coordinates are positive here and down here, but the crucial thing is that these have a mean of the middle, the 0, 0. So we would expect that either x to be negative and the y-coordinates be negative, or the x-coordinates positive and the y-coordinates be positive for a strong correlation. So, for a positive correlation. So for a positive correlation, we would expect the product of x times y to be positive. And clearly, for a negative correlation, then we'd want the product of x and y to be negative, less than 0. Why is that the case? Well, clearly, if I have anything in this quadrant or this quadrant here, then the x-coordinates over here will be negative, but y is positive. And down here to the bottom right, x is positive, but now this times y is negative. So clearly we want some kind of indicator that's checking whether the products are positive or negative. And luckily for us, we can work out that quite easily. And all we can just do with that is a good initial guess would be to just do the sum of x times y. Now the problem with that is, well, what's going to happen? Well, suppose this data is bounded between, let's say, 10, 10, and let's say minus 10, minus 10. Then our sum x and y's might be in the regions of the thousands or the 10,000s. It depends on the data set. However, what were to happen if this were to range in the hundreds, like so? Then, because there's products, it would increase by 100 and so on. And now we want our correlation to be a measure of how the data was represented as a straight line. So really, this number shouldn't change depending how I scale this up. So the way we're going to get around that is we're going to divide the sum of xy by, now this is going to be very tricky. We want to normalize this. We want to normalize this whole thing so that ideally our PMCC is trapped between 1 and -1. We're normalizing it. Okay, this normalization process means that this PMCC value has to be between 1 and -1. Okay. So, one way you can think about it is if we divide by the square root of the sum of x squareds and divide by the square root of y squareds, then this will work out. Okay. Now, here's a problem. We don't necessarily have the mean at the origin. For example, we might have our coordinate axes here and here. They might be like this, say. At which case, what do? And this is a fairly easy fix. All we need to do now is replace everything in here with some translation. And that's going to be relatively easy. So the sum of xy is just going to be, we're going to subtract the sum of x, sum of y over n, like so. This thing down here is going to become the sum of x all squared over n. And this thing is going to be minus the sum of y squared over n. And now we've got it. We now have a way of calculating our PMCC. Okay. So now, given any summarized data, all we need to do is that calculation, and we're away. You've probably seen these things already. I mean, for example, this thing up here is just s of xy. So that's the sum of xy minus the sum of x times the sum of y over n, where n is the number of points. Similarly, this thing down here is s of xx, which is the sum of x squared. So we take the x squareds and when we sum them, minus the sum of x, and then we square them over n. And then finally, we've got this thing here, which is SYY, and this is by symmetry going to be the sum of y squared minus sum of y all squared divided by n. Okay, so in other words, if I want to use my new lingo, the PMCC is just going to be the sum of SXY over the square root of, now because these are surds, I can now combine them. So now I'll put these two over here. SXX times by SYY, like so. Okay, that's a key result. I'm trying to think, it's been a while now. This, I'll put a dash because this is supposed to be in A-level maths. You're not supposed to be able to prove this kind of thing, although if you want to more generally prove it, you can start with this idea of what I've said over there and think about the quadrants being positive or negative depending on how you defined it. But yeah, to be honest, if you want to be more rigorous, I would look back at previous videos and look at the standard deviation and the distance from the mean, that kind of thing. and you can, I mean, it's an exercise for yourself. Can you formally prove why the formula of the PMCC is the way it is? I've just gone over it fairly briefly to give you more of an intuition. So, PMCC. What else can we do? Well, we can actually perform hypothesis tests. Okay, so hypothesis tests. Hypothesis. Can't spell. Hypothesis tests. Okay, really easy. This is an A-level maths as well, but the null hypothesis is always that there's no correlation. And by the way, the alternate hypothesis, these are always one-tailed tests. Okay, so H1 is there is a correlation, can't spell, correlation, between variable 1 and variable 2. It's not necessarily stating whether it's positive or negative. And the way it works is the following. Now, you are given in the formula sheet these critical values. You don't have to memorize these, you just have to look them up as and when you need to. So, it's really easy. Suppose I want to test at the 5% significant level whether a row value of 0.95 is enough evidence to suggest that there's a positive relationship, and let's say this was taken from a sample of 10 data points. Well, I look at the sample size 10, the probability of 5%, and I just see where they line up. And essentially this critical value of 0.5494 means that any probability above that, so since 0.95 is greater than 0.5494, then that means we accept H1 in this case, and that there is evidence to suggest correlation. If we had a correlation value that was lower than 0.5494, then we would accept H0 and say that's enough evidence to suggest there is no correlation, or rather there's not enough evidence to suggest a correlation. This P up here isn't actually a P, it's a Greek letter rho, as in row, row, row your boat. Yeah. So that's pretty much it for the product moment correlation coefficient. There's other things to bear in mind, for example, scaling, any kind of coding. So, you know, coding is not going to affect the correlation. Is it? Well, linear coding, think about it for yourself. It won't. It doesn't matter if you stretch out. So let's think about coding. Let's say y equals sum ax plus b. You do some transformation like that, and let's not use y. Let's use x prime. If you translate x to x prime, well, this adding b is just going to shift all the data points up or down, so that's not going to change anything. And this multiplying by a just means that the line is more spread out, but that just means you can imagine that your perspective has gotten smaller or bigger, and the correlation is going to be the same as well. If you want a more formal definition, I suggest you could play around with this stuff in here. But so coding will, or linear coding, by the way, linear coding will not make a difference to the PMCC. Couple of other takeaways. If you think about it, if you can prove that there is an existence of a positive correlation, then that means you're entitled to draw a regression line. Like, you have a justification to do that because there's evidence to suggest there's a positive correlation, a positive relationship. And, you know, same for negative correlation. If there's enough evidence for a negative correlation, then and so on. So okay, so how would you prove a negative correlation? Well, I don't know. Suppose okay, let's try a different one. Let's say from the results I got minus 0.62, and I want to test at the 5% significance level with a sample size of say 5. Then that's quite easy. I've got a sample size of 5 at the 5%, I cross it over and I get this, which is minus 0.804. Now minus 0.8054 means that I would have to be more negative than the minus version of that for there to be enough evidence to suggest it's a negative correlation. So in this case we'd accept H0 and there's not enough evidence. Okay, so whenever you want to test for a positive correlation, then you just read the table as is. If it's a negative correlation, then you have to be more negative. So what's going on is, imagine this is almost like a normal distribution like that, where zero's in the middle and all these values here, the negative one is down there and the positive one is up there, and the critical region is always in these outside bits. So if you want to test for a negative correlation, you look at that bit, and if it's positive, you want to check out the bit to the right. And yeah, that's pretty much it. Just be aware that exam boards like to mix and match these topics with various other things. For example, if you've used the PMCC to justify there's a positive correlation, then they might want you to then work out the linear regression, the equation of the regression line. To be honest, I haven't gone over what your calculator can do. There's two reasons for that. One, not everybody will have the Casio FX CG50, which I do actually recommend. I was a bit hesitant at first because I thought, oh, it's a lot of money, but actually it is worth it. And I think if you're going to be I think it's worth it, and it's essential if you're going to do A-level further maths and you're going to be doing the statistics course. I think when we look at the Poisson and the geometric and all that stuff, then yeah, it just saves so much more time. Okay. The second reason is I know how to output the PMCC on my calculator, and I've got a sneaky suspicion that it can run a hypothesis test with it, but I haven't quite figured that out. But at least I can talk through where it would be on the CG50. I do have a Casio FX991EX somewhere, and to be honest, it's all in the menu 7 statistics option, and you can play around for it. Or no, it's in the it's in menu 6 menu 6 spreadsheet, not spreadsheet, table function. It's definitely menu 6 because 7 is statistics and 6 is the one to the left of it in the grid. And then you enter in the data, and then you press Opton, and then you want 2 variable calc, and then you can look at the regression line, and it'll give the R value, which is rho in this case. So yeah, actually that's another good thing to clear up. So R is the PMCC for the sample, and rho is the PMCC for the population. So if you see R on your calculator, then don't panic. That's just the PMCC, but it's for a sample, and it's the sample that you've inputted in your calculator, because your calculator doesn't know that's the total population. Right. We've talked about hypothesis testing. We've done the PMCC and how to calculate it. Hopefully I've shown you where it comes from, and you can go off and explore that yourself if you wish to. I've got 3 examples that I want to go through. Hopefully today will be fairly short and sweet. Okay, so the blood pressures, P, milligrams per whatever that is. Interesting. And the ages T years of 7 hospital patients are shown in the table below. and blah, 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 blah. Find SPP, STP, and STT. Right, so various things you can do here. SPP is going to be the sum of p squared minus the sum of p all squared over n. So the sum of p squared is 106397 minus the sum of p, which is given as 833 squared all over n, and there's 1, 2, 3, 4, 5, 6, 7, so that's over 7, and that value is 7,270. STP is going to be the sum of TP minus the sum of T times the sum of P all over N. And that's going to be 42948 minus the sum of T, which is 341, times by the sum of P, which is 833, and this is all over 7. 42948, 341, and this apparently is 2369. Oh dear. What's going on here? 2369. And so I've done that one. I need ST of T. So that's going to be the sum of T squared minus the sum of T all squared over N. So the sum of T squared is given, which is 18181 minus the sum of T, which is 341, all squared that over 7, which is, oh, not a nice number, never mind, 1569.42857 and so on. So that's that done. So this is my answer for part A. And for part B, calculate the product moment correlation coefficient for this data. So the row value is just going to be S of TP over the square root of STT SPP. I always remember it's the one that's got two different things over the square root of the product of the things that have got the two same. So T and P are different, so PP and TT go on the bottom, TP goes on the top. So TP was what? 2369, and this is all over the square root of STT, which is the 1569 point stuff, times by SPP, which was 7270, and that will give you a value of, to 3 decimal places, 0.701. So this is a fairly strong positive correlation. So this would imply that as you increase T, then P increases as well. If you're interested, the blood pressures and ages, well, okay, T is the years is the ages of the patients. So I'd probably say that's the independent one. And that means the blood pressure is the dependent one. And now often the independent variable is called the explanatory variable. And the dependent variable is the control, not the control. It's just the test variable. Now there is a subtle difference between independent and explanatory. Independent variable is when that variable is completely independent. So the blood pressures depend on the age of the hospital patients, maybe, but the age of the hospital patients doesn't depend on the blood pressures whatsoever. I don't see how someone's age depends on their blood pressure. For example, if you manage to get your blood pressure down, that doesn't mean your age is going to change or go backwards in time. An explanatory variable is very similar. It's the one that's more independent, but it's in the case when it's not entirely clear that it's completely independent. In this case, clearly ages are 100% independent, but if you was forced to make a choice between which one is the explanatory variable or the test variable, And clearly you would pick T as the explanatory variable. Another way of looking at it is it explains what's going on. The age is the explanatory factor when it comes to blood pressure. Okay, so those are my answers. And we'll leave that one there. Okay. Next up. Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures W pounds and the average weekly temperature T degrees Celsius for 8 weeks during the summer. The PMCC for this data is minus 0.915. Stating a hypothesis clearly and using a 5% significance level, test whether or not the correlation between blah, blah, blah is negative. Okay, so the null hypothesis is that there is no correlation. And the alternate hypothesis is there is a correlation between, and then which one's the independent variable? Well, it's clearly T, degrees Celsius, temperature, and W pounds. Okay, so I've set my hypotheses out pretty clear. So let's recap. So alpha, the significance level is 5%. N, the number of samples, because this is bivariate data, is 8. They've done it for 8 weeks. And the test statistic we've got is minus 0.915, or is that. Okay, so that's the test statistic. Now what we need to do is look at the critical value for when N is 8 and the alpha value is 5%. So if we look up here, okay, so N is 8, we're going to trace over, so 0.6215. Okay, 0.6215. Right, it's 0.6215. Oops, daisy. So the question is, because we're testing for a negative correlation, okay, this low tail is minus 0.6215, was it? Have I read that right? 6215, yeah, 6215. And this region is my H0, and this region is my H1, and clearly minus 0.915 is way out here somewhere. So the conclusion is, except H1, there is evidence to suggest there is a negative correlation at the 5% level. Okay, easy peasy. Okay, B, suggest a possible reason for this correlation. Well, you just have a look at human factors, right? Tessa owns a small clothes shop in a seaside town. We've just kind of shown that the 5% level, that there is a negative correlation. So maybe, when it's hot, when temperature increases, people spend less on clothes, and because she lives at a seaside town, maybe they are at the beach instead of shopping. Who knows? Who knows? There's so many things you could put there. As long as it's a sensible reason, it doesn't particularly matter. I don't know. Maybe you could argue that in the summertime, people are more likely to wear shorts and bikinis or whatever, and they cost less than in the wintertime when people are wearing coats and jumpers and scarves and hats and gloves and stuff, and it just costs less. I don't know. Doesn't particularly care. As long as you've made some sensible suggestion, I don't see what the problem is. Tessa suggests that a linear regression model could be used to model these data. State, given a reason, whether or not the correlation coefficient is consistent. Yes, because minus 0.915 is fairly strong. So this would suggest a linear relationship is suitable. Remember, the PMCC can only have a value between 1 and -1. And so since minus 0.915 is pretty close to -1, bearing in mind -1 means there's a negative correlation, a perfectly negative one. +1 means there's a positive correlation. And if the PMCC is 0, that means the data is essentially random. There's no correlation. So, D, state giving a reason which variable would be the explanatory variable. Well, do you think the temperature depends on weekly sales, or do you think the weekly sales depends on temperature? Well, it's clearly going to be temperature because this is independent and explains the W pounds weekly sales. Tessa calculated the linear equation, blah, 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 give an interpretation of the gradient of this regression equation. Okay, so what does -171 mean? Well, that means every time I increase T by +1, that means W is going to go down by 171 pounds. So what this means is an increase of 1 degree Celsius results in minus 171 pounds loss of, is it sales or profit? Yeah, of sales W. So what this graph is predicting is every time the temperature goes up by 1 degree Celsius, you're losing out on weekly sales. Cool. Yeah, difficult. Do they want an interpretation of the gradient? No. When they say interpretation, what you're doing is you're playing the job of interpreter. Like, for example, if Tessa came to you with this problem, then it's your job to analyze the data and then make sense of it to her, just that she understands what's going on. For you to just say, well, there's a gradient of -171, she'd be like, well, what does that mean? What do you mean a gradient? How does that affect my business? Whereas if you try to explain to her that if for every 1 degree of temperature that goes up, that your weekly earnings is going to go down by 171 pounds. Okay. Right, last one. Pause the video and give it a try, should you wish to. Okay, Barbara is investigating the relationship between average income, GDP, gross domestic product per capita, ex-US dollars, and average annual carbon dioxide CO2 emissions, Y tons for different countries. She takes a random sample of 24 countries. Interesting, so immediately that tells me N is 24. And the coefficient between them, her rho value, or it should be R really because it's a sample, is 0.446. Stating her hypothesis clearly, tests at the 5% level whether or not the PMCC for all countries is greater than 0. Okay, so H0 is the rho value equals 0, i.e. there's no correlation, and H1 is that rho is greater than 0 and that there is a correlation. Okay, so we want the 5% significance level where N is 24. So unfortunately I have to go up to my table. N is 24 and on the 5%, so we're going to be 0.3438. 0.3438. Okay, 0.3438. So that means if I draw a little distribution, then the upper 5% here, this boundary is 0.3438, and my test statistic of 0.446 is clearly above this critical value. So that means we're going to accept H1, and therefore we're going to have, there is evidence at the 5% level that there is a positive correlation. Okay. So yeah, there does appear to be evidence that on the 5% at the 5% level there being a positive correlation. Okay, Barbara believes that a nonlinear model will be better to fit the data. She codes the data using the coding blah and blah and obtains the model blah. The PMCC between C and M is 0.822. Wow, that's pretty good. Explain how this value supports Barbara's belief. Well, look at it. What would change? I mean, it's still going to be n equals 24 because there's 24 values, and the critical value was 0.3438. But now her test statistic is 0.882, which means now that she's taken logarithms and transformed it, it's now an even better approximation for a straight line. So since 0.882 is stronger than 0.3438, it's justified at the 5% level, and since it's better than 0.446, it is a better representation of linear correlation. Okay, show the relationship between y and x, so this is part B, so that's done. This is all part A. Part C, show the relationship between I and x can be written as that, where A and N are constants to be found. Okay, this is just a logs thing, so what have we got? We've got C is log base 10 of y equals minus 1.82 plus 0.89 m, which is now log base 10 of x. Okay. Well, this isn't actually too bad. What I need to do is bring this up as a power. So this is log base 10 of x to the 0.89. And then if I add this over, this is log base 10 of y, and this equals minus 1.82 added over to there. So that's going to be plus 1.82 equals this. Now I can write 1.82 as log of 10 of what? So if I think about it, log base 10 of what equals 1.82, or 10 to the 1.82, that's easy to do. Mate, come on, 10 to the power of 1.82. So what goes in here is 66.07 to 2 decimal places. So this will be 66.07, and this will be log base 10 of y, and this will be log base 10 of x to the 0.89. If I add these two logs, I combine them, so that's log base 10 of 66.07 y equals log base 10 of x to the 0.89. And now they're both logs, I can now cancel, and now I can do y equals, and then I can divide by 66.07, whatever it was, both sides, and I will get y equals 0.0151 x to the 0.89. And now I have satisfied what it is. So it looks like A is 0.0151, and it looks like N is 0.89. If I wanted to give them to, well, if I wanted to give them to 2SF to match, then A would be 0.015. And both of these are to 2SF. Okay, that's pretty much it what I wanted to talk about today. The reason I haven't explained where these critical values come from is because we need to look at something called the T distribution. And I promise we'll be looking at that soon. I'm just trying to think, when is it we look at that? Going to be looking at the T distribution round about the 3rd, 4th, 5th, 6th, the 7th of August when we look at joint distributions and that kind of thing. But yeah, the student's t-distribution is something we need to look at first before looking at this. But okay, hopefully you found that interesting, and yeah, have fun.